If you look at any signal around you, the sound of my voice, the Wi-Fi beaming through the air, even the data zipping around inside your phone, they all seem incredibly complex. Almost chaotic, right? But what if I told you they're all made from the same unbelievably simple ingredient? Today, we're going to crack that code. We are uncovering the secret recipe that builds, well, just about everything in our modern world.
So here's our game plan. We're going to start by looking at simple versus complex waves, then we'll go on a hunt for clues, for patterns. And that search is going to lead us to this mind-blowing idea from a mathematician named Fourier, which reveals the secret recipe of waves. And then we'll tie it all together and see why this one idea is basically the backbone of all our technology.
All right, let's kick things off with a tale of two waves. And these are signals that are all around you every single day, even if you can't see them.
On the left, you've got this perfect, predictable, clean rhythm of a pure sine wave. Simple, elegant. And on the right, that's the waveform of a human voice. It looks like a total mess. It's chaotic, unpredictable, random. I mean, they look like they come from two completely different universes, don't they?
And that brings us to the core question for today. Are these two things truly different? Or is there some kind of hidden connection, a secret bridge between that perfect simplicity and all that wild complexity?
So how in the world do we start to unravel this mystery? Well, like any good detective, we start by looking for patterns. This is our very first clue to figuring out what's really going on inside these signals. And right away, that clue lets us sort all signals into two big families. First, you've got your periodic signals. These guys repeat the exact same shape over and over and over again on a fixed beat. And then you have the non-periodic signals, which, you guessed it, never quite repeat themselves. They're always changing, always evolving.
And this shows that difference perfectly. The sine wave and the square wave, totally predictable. Once you see one cycle, you know exactly what's coming next forever. But a voice signal, it's always different. Same thing with a stream of digital data. Now, the individual pulses might look the same, but the sequence of them, the actual information, is non-repeating. There's just no simple pattern to lock onto there.
Okay, so we can spot a pattern. That's a good start. But, it's not enough. To really get what a signal is about, we've got to be able to measure its strength. And this is where things start to get really interesting.
Let's go back to that simple, clean, periodic sine wave. Now, if you were to measure its value over one complete up and down cycle and then calculate the average, what do you think you'd get?
The answer? 0. A big ol' 0. Why? Well, think about it. For every positive peak, there's a perfectly matching negative dip. The top half and the bottom half just completely cancel each other out. So the average is 0, which doesn't really tell us anything useful about the wave's power, does it?
So engineers came up with this really clever workaround. It's called the rectified average value. And all it is you just take that negative bottom half of the wave and you flip it up so it's positive. And just like that, you can calculate a real, meaningful average that isn't 0. Pretty neat.
But the one that really matters, the most important measurement of all, is the RMS, or root mean square value. This tells you the wave's true effective power. The easiest way to think about it is this. It's the DC voltage that would give you the same amount of heat. It's the real-world measure of how much punch that wave is actually packing.
And all of this, thinking about patterns, figuring out how to measure things, it all sets the stage for the big reveal. This is the moment. The groundbreaking idea from a guy named Jean-Baptiste Fourier that totally flipped our understanding of signals on its head.
And there it is. That's it. That's the secret recipe we've been looking for. Any repeating wave, I don't care if it's a square wave or some jaggedy, distorted, messy-looking thing, it can be built by just adding together a bunch of pure, simple sine waves. That chaotic-looking signal from before? It's not chaos at all. It's just a bunch of simple waves wearing a clever disguise.
And you can actually see it happen right here. It's incredible. We start with one main sine wave, right? Then we add another one that's got a higher frequency, and another one that's even higher. And look, just look at what happens. As we keep adding more and more simple sine waves, their sum starts to morph, and it magically builds a square wave right before your eyes.
So, if any complex wave is really just a recipe, then what are the ingredients? Let's open up the cookbook and break down the components that Fourier was talking about.
Okay, every good recipe starts with a main ingredient, right? For a waveform, that's called the fundamental. It's the sine wave with the absolute lowest frequency in the whole mix. This is the one that sets the overall rhythm, the repetition rate of the final wave.
You can think of it like the bass note in a musical chord.
And then you add the harmonics, and these are the flavorings, the spices. They're also pure sine waves, but their frequencies are perfect whole number multiples of that fundamental. So 2 times the frequency, 3 times, 4 times, and so on. And it's the specific mix of these harmonics, which ones you use and how strong they are, that gives each complex wave its unique character, its unique shape.
So you can see how it all just stacks up. You've got your fundamental frequency, let's call it F. That's your bass note. Then you layer on the second harmonic at 2 times F, the third harmonic at 3 times F, and you keep going. Each one adds another layer of detail, sculpting the wave into its final shape. Okay, so this is a really cool math trick. I get it, but so what? Why should you care about any of this? Because this isn't just theory. This secret recipe is literally the invisible code that runs our entire modern world.
The truth is, our world runs on these complex, non-sinusoidal waves. Those sharp square waves coming out of the power inverter that charges your laptop, the rapid-fire pulses of light carrying data through fiber optic cables, even the distorted, messy currents that our electronics draw from the wall, none of them are simple, clean sine waves.
And knowing their recipe, that's everything. In power systems, it lets us filter out nasty harmonics that can destroy equipment. In signal processing, it's literally how your phone separates your voice from all the background noise. It is the absolute key to designing efficient electronics for electric cars and the powerful machines that run our industries. Fourier's recipe isn't just an idea. It's the tool we use to build and control our entire technological world.
So what's the big takeaway here? We've seen that even the most complicated, chaotic-looking signals are actually made from incredibly simple ingredients. And that leaves us with this one kind of mind-bending question. What other complex patterns out there, in the stock market, in the weather, maybe even in the firing of the neurons in our own brains, are really just simple waves in disguise, just waiting for us to find the recipe?